Okay, so let's start. Welcome to this last seminar of this academic year that will be presented by Modeste. Well, there will be some changes. We'll have a break now in August, and we'll start over again in September. And there will be some changes in the organization that will be announced shortly. So that's all. And today we have Modeste, all of you know already from IFISC, that will tell us about dispersion effects on broadband.
Thank you very much for introducing me, and thank you for coming. I know we are close to the and maybe you are tired. My talk of today is the continuity of what I introduced here some months ago. And the title is Dispersion Effect on Broadband Communication implemented by Electro-Optic, non-linear delay phase dynamics. I was lucky to work with all these people, and I'm really happy to present you some results that we found out. The outline of the talk is divided in two main parts. The first is the dispersion effect in chaos communication. In that part, I will talk about the effect of dispersion in single-mode fiber. Then I will introduce some management techniques to get around the dispersion. First, I will talk about the dispersion compensation in fibers. Then I will also talk about the dispersion shifted to fiber. In the second part, which is a little outside of the title, I will talk about the influence of the message on time-domain identification. And in that part, I will first have some slides about to introduce that part. Then I will report some results of the phase analysis. And finally, I will report the result from the real detection power in the phase generated. In the phase chaos. By the end, I will give some conclusion remarks. Let's start. What is the dispersion? The dispersion is the time domain spreading or broadening of the signal as it travels through the fiber. This is caused by the fact that all light sources used in the optical communication emit light not at a single wavelength, for instance at lambda 0, but in the band of the spectral weight like this. And different wavelengths in the band travel at slight speed and finally arrive at different times. This lag at arrival is called the differential delay. And for instance, here we have this, and at arrival we can have this, where the spectrum is more straight. And to understand how this reacts in optical communications, I can show this example, which consists in sequence of 0 and 1 to be transmitted through the fiber. So for this, let's say we have this original bit to be transmitted through the fiber, and then after some kind of propagation, the differential delay is created like this, and they recover data. For instance, in this case we have 0 and 0 here, then 0. And in some cases, like the third one, we have 0 and then 1, and we have here 1 instead of 0. And finally, among 9 bits which have been transmitted, we have 6 current bits and 3 round bits. So now, if we plot the dispersion as a function of the wavelengths, we will see here what is the evolution when we go from the wavelength to another. I will first recall that the total wavelength, the total dispersion is the balance one between the material wavelength dispersion and the wave dispersion. And the zero dispersion here is obtained at 1.3 micrometer, but at this wavelength, the losses are higher, so we cannot emit at that wavelength. In general, optical communications emit at 1.55 micrometer, and at that wavelength, we should face up the dispersion, which is 20 picosecond square per kilometer, and we should also face up the losses of 0.2 dB per kilometer. And besides this, we should also face up the non-linearity in the fiber. So we are going to see how this react in chaos communication, and for that reason, the signal that we are going to analyze was generated from this phase chaos generator, which is composed with the phase modulator, and the role of the phase modulator here is to convert this voltage into the phase, which is delayed in time, travel through the fiber, and later convert into the intensity, travel the imbalance Mach-Zehnder interferometer. The output is detected using a photodiode, and then apply back to the filter, which is considered in this case as the first filter, bandpass filter. So now the equation of the dynamics of the system is ruled by this equation, where tau and theta are the high and the low characteristic and response time of the filter. J here is the gain, the overall gain, which in experiment is done to obtain to get the different regime in the system. The tau T here, capital T here, is the time delay, and capital T plus delta T is the second time delay in the system. Phi is the static phase of the Mach-Zehnder interferometer. Now, we can choose this scheme because of some properties which have been already found out. And among these properties, we found the capability of the system to develop complex counts with good properties. We found less sensibility to external exhibitions. There is no interference between the message and the carrier. Also, a large message, the large amplitude message can be integrated through this scheme. And finally, because demonstration was done, have been already done using 10 gigabytes per second message in stellar optic network structure. And this structure was the Frère Lumière in France.
What is Frère Lumière?
Frère Lumière is in French, and
where is it? What kind of network is that?
I don't really know why they chose this name, but I don't know if the translation, I can translate this from French to English, but I don't know if it's important.
It's in Besançon actually. The brother Lumière are the one who invented the cinema, and they are all in Besançon. So we have an optical network, which was called Frère Lumière network, but it's in the memory of these Lumière brothers.
Okay, thank you. So, the full experimental setup is this one, where we can distinguish three blocks. The first block is the emitter, the second one is the fiber, and the third one is the receiver. So, the fiber here is modeled like with the non-linear equation with parameters of losses, of chromatic dispersion, and the nonlinear factor. Now, when we launch, when a coupler is used to transmit a part of the signal generated through this transmitter, and the output of the fiber is sent through the receiver after compensating for the losses. So what we are going to do, we will analyze the signal at the output of the filter as the synchronization error is concerned, or at the output of the, after the cancellation, after the Q's cancellation, as the spectrum is concerned. So, to measure the synchronization performances, we have used the synchronization error defined as this one with the fiber parameters which are here listed. So, we have reported the synchronization error as a function of the length, the fiber length, for different cases, which are G equal to 2.5, corresponding to the single scales, and G equal to 5, G equal to 3.5, G equal to 5, which is the high complex scales in this case. Okay. So, in this case, what we can see is that the dispersion increases a lot with the, as a function of the fiber length. We have here only 10 kilometers of fiber, and then we have a dispersion which is close, and then we have the synchronization error which is close to 100%. So, in a real optical complications, we can the synchronization error could not be exceed 20%, and when we exceed 20%, we say we don't have a good, we cannot properly retrieve the message. And for that reason, I will suppose that I will assume that 20% as the threshold below which the synchronization is accepted. So now, if we consider this hypothesis, we can see that in this case, the synchronization error is accepted below 4 kilometers of fiber propagation. And for this, we have, in order to compare these results with the experimental one, we have plotted some spectra, and which are here, and we have first considered the pair of back-to-back configuration, which means there is not, we didn't account for the fiber effects. And in this case, we can see that the spectrum that we have here is due to the noise and to the not incorrect matching between the emitter and the receiver parameters. If we consider the case in which the line is equal to 1 kilometer, we can see here that we have a good cancellation in blue. We have a good cancellation from 2.5. This is for G equal to 2.5, and this is G for G equal to 5. And if we increase the length to 3 kilometers, we will see that if after 7 gigahertz, the cancellation is not begins to feel the dispersion, the fiber effect in this case, in the case of 3 kilometers. And for 21 kilometers, we can see that the cancellation is practically destroyed in both cases. So, numerical results show more or less the same result, with the difference that in this case, the spectrum are more spread, and this is due to the fact that the filter used in experiment is in the higher order. Is more than one order considered in numerics, because in numerics we assume that the filter is in the first order, and in experiment this is higher than the first order.
Sorry, have you explored the oscillation you see on different spectral curve? It should be related to delay mode free spectral range, but in fact we don't see them everywhere. So do you have any reason for that?
Yes, because I found some. I was trying to make some connection between these things and the delta T, and what I saw that it does not correspond really to delta T. And really, I don't know why these peaks are.
But still to be
Yeah.
explored.
So I have not yet to do this. Now, what we do here is trying to get around the dispersion because, as I said, if we are above 20% of synchronization error, it means we cannot retrieve the message and we should get around this problem. And the possibility, and which is also the word used in current communication, is to compensate for the dispersion after some propagation, after some fiber learn of propagation. What I will say here is, for instance, we are trying to compensate for the differential delay, and for this reason we keep propagating the signal over some distance of standard mode of standard fiber, and then we use dispersion compensating fiber, or we use dispersion compensation modules to lower, to cancel this differential delay, and this is repeated throughout the fiber, throughout the length. So cancel the differential time delay means cancel the dispersion. And in this case, what we do in numerics is to have this relation allows to have the length of the dispersion shifted fiber, which will help to compensate for the dispersion. For example, where I have this D1, this is the dispersion parameter, and this is the length over which the light will travel in the single mode fiber. And then to search for a dispersion shifted fiber length, I will go from the dispersion in that fiber. For typically, the dispersion in dispersion shifted fiber is 10 times the dispersion in the real in standard fiber. And for this reason, if I have, for instance, 50 here, I should have 5 here to have 0 to follow, to check, to fulfill this relation. We have performed some results concentrating only on one portion of this, and here you can see that the synchronization error after propagating the signal over 50 kilometers of fiber and then use 5 kilometers to compensate for a dispersion here, we managed to lower the synchronization error at the acceptable value in this case. And this is independently for G equal to 2.5, for the gain equal to 2.5, or the gain equal to 5. And what you see here is due to the fact that in addition to the chromatic dispersion, there are nonlinearity in the fiber, and there is also the dispersions which should be taken into account. So if we do again the dispersion, the cancellation, we will see that what we do here in experiment is not to use the dispersion compensating fiber, but we use dispersion compensation modules, and to compensate for a dispersion over 22 kilometers of propagation in single mode fiber, we turn the dispersion compensation module to minus 360 picosecond per kilometer, and to compensate for a dispersion over 50 kilometers of propagation, we turn to 880 picosecond per nanosecond. In this case, you can see that in all the cases, we managed to cancel, to have good cancellation, as you can see here, for Okay, you can see here, and also from the numerics. And from the numerics, what we do is to use this relation. For 20 kilometers of single mode fiber, we use 2 kilometers of dispersion compensating fiber, and for 50 kilometers of single mode fiber, we use 5 kilometers of dispersion compensating fiber. Now, I want to introduce another method which can be also used, and this is the dispersion shifted fiber. And it is characterized by the fact that instead of having the zero dispersion at 1.3, like it is the case for the single mode fiber, the zero dispersion is shifted at 1.5 at 1.55 micrometer, and all other parameters will change.
No, because there you have a minimum losses also.
Yes.
At 1.55, you do the shift because the losses are minimum there.
Yes, and all the dispersion is shifted.
Dispersion is shifted, but you want that point because losses are lower.
Okay. We have the performances of this fiber will depend on how close the dispersion, how close the lifted wavelength is compared to the zero dispersion wavelength. And we consider that if we are not able to emit at zero dispersion wavelength, we can have some dispersion. And if we consider, for instance, the case of 0.2 picosecond square per kilometers of chromatic dispersion, we can see here how the synchronization error increases with the fiber length. And what is important here is that we see 15% of synchronization error is reached here after 40 kilometers of propagation. And if we are able to further lower this value to 0.1, we can see that with the same parameters, we have the 15% of synchronization error after 100 kilometers of propagation. If we have also plotted the cancellation, the spectral cancellation for this case, and what we can see is that in experiment we did this using 22 kilometers of dispersion shifted fiber, but in numerics, what I consider is 0.1 as the 0.1 picosecond square as the chromatic dispersion. And in both cases, you can see that the cancellation is good.
Sorry, is there any reason why the range in X is different in both graphs?
Yeah, here is 20 and there is 40. This is due to the fact that in numerics, we assume that the filter is the first order filter. And in experiment, you can see of B, the first order is higher than the first order.
Yeah, but if you've got the same range, they won't look so nice. The comparison will be worse.
Yes, you can plot, but you will not have the same dB. The same in the vertical axis, you will not have the same orange chart. To summarize this part, I will show the IF diagrams of all the cases that we have visited. And the first one is for the original message. If we have the original message correspond with the corresponding I diagram after propagating over 21 kilometers of fiber, of the standard fiber, we will see that the I diagram here is closed, it's completely closed. It means we cannot recover the original bits from here. And now, if we propagate the same signal over 50 kilometers of fiber and then compensate using 5 kilometers of dispersion, compensate in fiber to compensate for the dispersion, we can see here that the I diagram looks like the original one. And the same case is is seen here for dispersion shifted fiber over 55 kilometers of propagation. So let's move on the second part of the talk. The aim of this part is to see, because what we have studied in the first part was the signal generated from the optoelectron phase fields, and I gave some motivation of choosing this. Now we are going to see how possible is to identify the time delay in this field. And mainly we will see if the message has a role in that identification. And to understand this, I would like to introduce some methods which are currently used to identify the time delay in the late system. The simplest one is by computing the autocorrelation, and we can also see that we can also identify the delay from mutual information, from filling factor, from distribution of extrema, or from forecasting error of the nodes. And more recently, another method was found here at IFISC by Luciano, and that method is the perturbation entropy. And before proceeding for the identification of time delay in this system, which are the one that we are studying, I would like to first see if the same works in the previous scheme, which is the intensity field. This one is the phase field, and this is the intensity field. I will not go in deep detail in the equations, but I will just say the nonlinearity here is implemented by the Mach-Zehnder modulator here, and the message is act as similar to the carrier. And if we don't account for the message, the system is described by this equation where X is the output of the feedback. And if I account for the message, in this case having an amplitude alpha, I will see that the part to be transmitted to the receiver corresponds to this one. In the second scheme, I will talk about the phase field generator, and in that case, I have already given some indication about this one. And what I would like to add is that the signal to be transmitted in this case is this one, which is the electric field. The electric field is this one. And you can see that only the phase here is chaotic, and the message is also integrated in the phase. And when I'm transmitting, I will say the overall phase to be transmitted is the carrier and the message. And in that case, what is important is that you cannot proceed for detection, direct detection, like in this case. What you have to do is to use, for instance, the Fabry-Perot interferometer, or to use the invariance Mach-Zehnder interferometer. In this case, we have used the Mach-Zehnder interferometer like this before detecting the signal. So this result was these two schemes were analyzing using these two methods. The first one is the autocorrelation, and the second is the mutual information. And what is important here is to know that at the time delay, the autocorrelation gives a peak or a value, while the mutual information gives only the peak at the time delay. So what we are going to do is to search for that peaks at the time delay. That is why the result will be reported only close to time delay, because we already know what is our time delay. So these results were obtained from the intensity curves. And the first, as I said, the signal to be transmitted is this one. And if we plot the autocorrelation without the message here in blue, we can see that the time delay is more close. The time delay, the peak is located here, more closer to the time delay, which is 30. And For one, I have considered the message with the maximum amplitude because I have considered alpha equals to 1. It means the message has the amplitude of 5, which is the maximum for this case, because the carrier also the gain is also 5. And if I consider the message at 1 gigabyte per second, I will also see that the time delay is located at there is a value here at around the time, I will say closer to the time delay. And for G equals to, and for the message at 8 gigabyte per second, I can see that this is not in red, it's not clearly located, identified. But if I plot the mutual information, I will see that in all the cases, I'm able to say that the time delay is 30 or closer to 30. This case is to see, what we are now going to see is to see if in the first use we have the same result or if there is something different from this case. Before proceeding for the real detection in the first use, I would like to just only focus on the phase. But this is not practical because you cannot, if you transmit the signal, you cannot only extract the phase. But I prefer to do this to see what is the effect of the message on the time delay identification. And for this reason, I will also consider 3 cases. The first case is without the message in blue, in black, the message at 1 gigabyte per second, and the last in red will be at 10 gigabyte per second. And from the autocorrelation, I see that I have the message. I'm able to locate it, to locate the time delay around 30 using when there is not message in blue and when there is a message with 1 gigabyte per second. And for 10 gigabyte per second, message with 10 gigabyte per second, I can see that the message is not properly, the time delay is not properly located here. But using the autocorrelation, I can also confirm that the time delay can be located from when there is not message in blue and when there is a message at 1 gigabyte per second. And I can also find small bit for the case of 10 gigabyte per second. And this
just to understand correctly, this point and picosecond offset between 2 peaks, that's the imbalance of your Marzenda for detection, or where does the difference of the 400 picosecond come from?
No, this difference, yes, is the local time of the...
It's the imbalance of the Marzenda.
Yes. This is located at capital T, and this one is at capital T plus delta T.
Okay.
And the previous one you showed was for the intensity chaos.
Yes.
So here you don't have any problem of the, you have a slightly shift of the maximum due to the inertia of the system, but then here you don't see that.
Yes, because...
Yeah, the peak is clear at third, yeah?
Yes, because
But before it was not.
in the previous, this was done around 29.8. And in this case, it's not the same.
So the inertia is much smaller.
Much smaller inertia in the phase that was
Yes. Here is also the case. The point is that the previous was done in the few range and this less than this one.
So the scale, the horizontal scale of this one is more.
It will be 1/10.
And then you see a little bit of inertia. But forget inertia, the point is where you can detect the time delay or not. Clear without message, you can detect the time delay in any system. Because this is, when you add a message,
you don't see that.
in this case, you don't see the network.
Okay, and looking at this result, we ask another question, which is to know if the view rate plays a role in time delay identification. And for that reason, we plot here the peaks, we record the peak and the time delay. And in blue, there is an extra condition to make this more clear. And this condition, for instance, is to define the mean value of the maximum for instance, we have this fluctuation, like the background of the autocorrelation or the mutual information, and we try to see, we define the mean value of around this fluctuation. We record just only the extrema, and then we define an error, which is the deviation, and this is to see if the peak is in the range of the fluctuation. It means we cannot distinguish the peak at time delay from other fluctuation. And if the peak is out, for instance, here, it means this peak is distinguished compared to the fluctuation. And it's what we use here. This is the mean value, and this is the error defined around the mean value. We record the peaks in black at the peak at T, and in blue, I plotted the peak at T plus delta T. And what we see here is that if for some bitrate message we can identify the time delay because the peak will be out of the range, and for someone we are not really able to identify. And in this case, we can also see this in the mutual information. From the mutual information, we can also see that these peaks can be identified, and after this, we can still identify that the amplitude is shorter. And we ask ourselves if this is due to the local time delay, delta T, and we have found that when we consider when we increase the delta T, this also increases. If instead of F is delta T equal to 0.4, as it is the case here, if I have, for instance, 1 nanosecond, I will see that this is also lower the system. So this finally, I found that this is due to the fact that this is due to the local time delay. And now, I would like now to report the result about the real detection in the system. Because before showing this result, I see that this was also to see the effect of the message. And now, if we want to see what an eavesdropper is really able to do, we will analyze the real detection of the real detection. Because we suppose that the eavesdropper is able to put the interferometer or the fabric to have the power, the fluctuation of the signal, and that fluctuation will be given by this formula. And if we compute again the autocorrelation, we will see that the time delay can be identified when there is not message, and when there is a message at 1 gigabyte per second, instead of identifying the two time delay, we managed to identify only one of the two, but we are able to see this value. And in red, corresponding to 10 gigabyte per second message, we see that we are not able to identify the time delay. And surprisingly, in the case of the mutual information, we are not able to identify the time delay, even for the case without the message. And I say surprisingly because in most of the papers, I saw that the mutual information is more precise than the autocorrelation. But in this case, we have found, and we have also used the perturbation and probing, and we found that in that case, we are not able to identify the time delay. We have also recorded the peaks, and in this case, from the autocorrelation, we confirm that this, before if we have the message if we have the message with the bitrate less than the inverse of delta T, we cannot identify the time delay, and you can see here the inverse is 2.5 megabyte per second, which is here. And of course, in this case, nothing is seen. So to conclude, I will focus on 3 points. The first is the transmission. I will just recall that using the single mode fiber, we cannot operate the chaos communication at for long distance. And the second is the dispersion shifted fiber and dispersion compensated fiber or modules can be used as an alternative to get around the dispersion. And finally, I will say that is using electro-optic phase cubes generation, it is possible to cancel the time delay. To cancel the time delay. Thank you for your attention.
There have been many studies in the past. Actually, Per and I have studied the effect of dispersion in chaotic waveform, but in the group in Athens, they did so many publications studying post-compensation, spectral inversion, many different techniques to study the propagation of the chaotic waveform. What is different, or what do you find is different with this scheme that was not the one studied before with respect to the optical?
Okay, thank you. In this case, the main point here is that we record the numerical result and also the experimental result. And what was done without the experiment. And at least for the case of the phase cubes. Because
well, but that, I mean, there are many experiments also. Because, for example, the experiment in Athens, when we published our paper, it has compensation. Because without compensation, as you said before, without compensation, you cannot extract any. So, actually, I think there we use a pre-compensation before, because you can pre-compensate, then transmit, and then detect. Or you can transmit, post-compensate, and detect. That has been studied also experimentally, but it's not the same. But I feel that the results are not very different.
Yes, to me it's different because from the moment that we have the phase cubes, we cannot predict using the intensity cubes.
Yeah, but the dispersion does not depend on the intensity. That depends on the wavelength and the frequency, but not on the intensity itself.
Yes,
there is the dispersion, the nonlinear effects. I mean, it's true that you have to compensate the dispersion.
Well, especially the linear effect, that is the most important in transmission, because nonlinear is not so important.
That's right, but the point is the purpose of this is that to see what is basically the combination of the nonlinear effect plus the dispersion plus compensation in phase chaos and compare with experimental results in fiber propagation. Now, if your point is that you can achieve 50 kilometers with compensation in phase chaos and in other kind of chaos, yes.
I mean, it's not very different to. You don't know what to.
If by different you mean that in one you can achieve 50 kilometers plus compensation of the dispersion 55 or total of 50 kilometers, and in the other 50 kilometers of all that. That's true.
The numbers depends on
the numbers depend on for a given fiber, you basically see the same kind of problems in both cases. But we have not done a careful measurement of the two systems in a system fiber. I would like to do that. To see really you do exactly the same fiber with the different kinds of chaos, if you really can push, but the difference could be almost maybe 10% of the different one. Because the difference, as you say, is not the most important role is a linear one, which is the dispersion, and the nonlinearity is not quite much at all. So then, whether you use one kind of chaos or another one, if you compensate the linear dispersion, it's basically the same.
Certainly, dispersion of shifted fibers are the best, but you will not convince any company to change the fibers just for that. That's the main problem, I think.
Yes. This is very bad. Just to answer rapidly, practically what people are doing is just to use this dispersion compensation rule, which switch outputs at the receiver side. And we showed that experimentally it was also the needed way to compensate the dispersion effects. And I think maybe one of the difference of this work is also to have really in a single paper at least a few indicators of the conversion between theory and experiments. In the previous paper, there were mainly, if it was experimental ones, some indications about, okay, we did dispersion compensation, it worked, and the other paper was purely numerical ones, or theoretical ones, and they did, okay, we implement the standard equations, and it should work. But here, it's really a joint theoretical and experimental work. And we try to recover actually qualitatively, and maybe for some issue quantitatively as well, some very corresponding methods.
Technical compass theory is also using different kinds, different parameters for the kill. So it's less good.
Yeah, I know. That's
There's a systematic study for all the systems. You know that, of course.
Okay.
Very good.
No problem. I would like to understand the mechanism behind why the delay time is being concealed in your phase chaos scheme. So what would be important is information. How does the magnitude of the message phase that you put on top compare to the fluctuations of a chaotic carrier in phase? And maybe you can also, that would be one indication, or do you think it's a different mechanism which really conceals the phase in autocorrelation, and it is just hidden autocorrelation, and would you expect it to find it in a different way? Because what certainly is clear is that it's important that the phase message changes faster than your imbalance of the detection.
I think the reason is because in the case of the Mach-Zehnder, we have the change which is faster than the message, which is faster than the change of the Mach-Zehnder, because we saw that below this value we can still see the time delay. But for instance, what I found in this case is that if you plot the mutual information, you will see the time delay of the additional Mach-Zehnder and not the real time delay in the system. And this is because the Mach-Zehnder is just for the detection. But if you get to compose all the dynamics in the system, you will not be able to.
And what's the magnitude of the message compared to the magnitude of the chaotic phase fluctuation?
The amplitude of the message is 1.5 because it's pi over. After modeling the system is pi over 2.
Okay.
And the amplitude of the fluctuation is 2.5 of x is 2.5.
Okay. Very good then. So let's say thank you for coming. I think there is no coffee to this.
What?
The